When you open a gas cylinder, you expect one thing, gas. But this cylinder gave no hiss, showed no pressure, and was still heavier than an empty one. Where had the gas gone? In a laboratory in New Jersey, that impossible result stopped a routine experiment cold. The cylinder had been filled with a colorless gas, sealed, and set aside while chemists tried to make the gas behave differently. When they returned, it appeared empty. No pressure, no visible liquid, no obvious residue around the valve. The experiment seemed to have failed so completely that there was almost nothing to record. Then someone lifted the cylinder. It was heavier than it should have been, not by a dramatic amount. Just enough to turn routine cleanup into a second look. Inside that cold, quiet metal shell, the missing gas had not escaped. But what had it become? The man confronting that mystery was Roy Plunkett, a young chemist working for DuPont at the Chambers Works plant in Deepwater, New Jersey. In the spring of 1938, Plunkett and his assistant, Jack Rebach, were pursuing a practical problem, finding a safer refrigerant. Their candidate was tetrafluoroethylene, a colorless gas stored under pressure in small metal cylinders. The plan was straightforward. Fill a cylinder, chill it, and allow the gas to flow through the equipment, then measure how it behaved. Nothing about the procedure suggested a discovery. It was routine laboratory work, repeated one cylinder at a time. But one morning, a cylinder refused to cooperate. The valve opened, yet no gas emerged. Plunkett checked the fittings. Rebach checked the apparatus. There was no hiss, no sudden release, no obvious leak. The cylinder seemed sealed, but it also seemed empty. That made no sense. A pressurized cylinder containing tetrafluoroethylene should have announced itself the moment its valve was opened. If the gas had leaked, the cylinder should have lost weight. If it had remained inside, the pressure should have forced it out. So they weighed the container. The scale gave them the first hard clue. The cylinder was not empty at all. It was slightly heavier than an unused one, as though some invisible cargo had changed form without leaving the metal shell. Plunkett and Rebach turned the cylinder in their hands. Nothing moved inside. There was no liquid sloshing at the bottom, and no visible cloud behind the valve. Only the dull rattle of something fixed to the interior, if there was anything there at all. They could not inspect it through the narrow opening. The only way to find out what had happened was to cut the cylinder apart. That was not a casual decision. The container had held a reactive, pressurized gas, and a cutting tool could turn an unexplained laboratory failure into a violent accident. But the cylinder had already become the experiment. With proper precautions, they opened the metal shell and exposed its inner wall. A pale, waxy coating covered the inside. It clung in sheets and rough patches, stubbornly attached to the steel where the gas had once occupied empty space. This was not frost. It did not melt away in their hands. It was not residue from a spilled liquid or a dirty container. The gas had not leaked through the valve. It had not vanished into the room. Somehow, inside a sealed cylinder, it had built a new substance and left the evidence stuck to the walls. The substance had a name, polytetrafluoroethylene, or PTFE. The gas inside the cylinder was tetrafluoroethylene, a molecule built from carbon and fluorine. Somehow, those molecules had linked together again and again until the gas became a solid coating clinging to the metal walls. The cylinder was not empty because of a leak, and the experiment had not simply failed. The gas had been transformed into something that barely reacted with anything around it. It was slippery, heat-resistant, and extraordinarily difficult to attack with chemicals. No one had set out to create it. No one had even known it was possible. Years later, DuPont would give PTFE a shorter commercial name, Teflon. But in that first cylinder, it was still an unexplained white solid, waiting to reveal why it was so difficult to destroy. The clue was hidden in the way the solid had formed. Inside the cylinder, countless small tetrafluoroethylene molecules had joined end to end, like links snapping into a chain. Each molecule carried 2 carbon atoms and 4 fluorine atoms. Under the right conditions, those double-bonded molecules opened up and connected, again and again, until a few simple ingredients became enormous PTFE molecules stretching through the white mass. The change was not just a pile of molecules pressed together. It was a new architecture. Along the center ran a tough carbon backbone, while fluorine atoms wrapped around it like a dense protective sleeve. They crowded the outside of the chain, leaving very little of the carbon skeleton exposed to the surrounding world. That shell explained much of the mystery. A carbon-fluorine bond is exceptionally strong, and the fluorine atoms held tightly to the backbone. Heat, moisture, oxygen, and many reactive chemicals could reach the surface, but they found no easy opening. The chain did not offer many loose chemical handles for another substance to grab. In ordinary plastics, acids or solvents can sometimes break the links, soften the material, or pull its molecules apart. PTFE resisted those attacks because its carbon skeleton was buried beneath fluorine, and because the chain itself was already extraordinarily stable. Household acids, industrial bases, oils, and common solvents could sit against it without producing the dramatic swelling, dissolving, or corrosion seen in other materials. A glass jar might cloud, a rubber seal might crack, a metal surface might pit. PTFE often simply remained where it was. That resistance had a physical side as well. The fluorine-covered surface held onto other materials very weakly. Water gathered into beads. Grease slid away. A drop of cooking oil could move across the surface with almost no hesitation because the surface energy was extremely low. The molecules at the exterior had little desire to bond with molecules from outside. This was why the material felt almost unnaturally slippery. The effect did not come from a liquid coating that could run off or wear away. It came from the outermost atoms of the solid itself. When two surfaces pressed together, PTFE offered very little molecular attraction between them, so they could move past each other with remarkably little friction. The same shield that made PTFE hard to attack also made it hard to use. Ordinary adhesives depend on a surface they can wet, grip, and chemically interact with. PTFE gave them almost nothing. Glue spread into droplets, or peeled away in a thin sheet. Paint struggled to form a lasting bond. Even when another material was pressed firmly against it, the contact could remain surprisingly weak. Heat created another problem. PTFE could tolerate temperatures that ruined many ordinary plastics, but it did not behave like a convenient wax that simply melted and flowed into a mold. As it softened, its melt became extraordinarily thick. It resisted movement, resisted mixing, and resisted the quick shaping methods used for common plastics. Manufacturers could not just pour it into a mold and wait for it to cool. They had to compress fine PTFE powder into shape, then heat it carefully until the particles fused into a solid body. The process was closer to sintering ceramic powder than molding a typical plastic. Every corner, hole, and thin section required planning before the material went into the furnace. Even cutting and joining demanded special treatment. Tools had to deal with a material that was soft enough to deform yet resistant to ordinary bonding. Engineers could roughen the surface, use mechanical fasteners, or chemically alter the outer layer. But the easy industrial shortcuts, melt, pour, glue, paint, were mostly unavailable. That contradiction defined the new substance. The carbon backbone gave it strength and continuity. The fluorine shell made that backbone difficult for chemistry to reach. Together, they produced a solid that resisted heat, corrosion, friction, and attachment with the same quiet efficiency. The cylinder had not contained an empty space after all. It had contained a material whose greatest talent was refusing to participate. And that refusal was exactly what engineers needed wherever machines, chemicals, and extreme temperatures met. The first people to recognize its value were not cookware manufacturers or plumbers. They were engineers facing a substance that could attack almost everything they had. The year was 1942. Across the United States, laboratories and construction sites were being pulled into the Manhattan Project, the secret wartime effort to build an atomic weapon before Nazi Germany could do the same. One of its most difficult problems was not the bomb itself. It was separating enough uranium-235 from ordinary uranium to make the weapon possible. At Oak Ridge, Tennessee, engineers built the K-25 plant for that purpose. Inside its enormous gaseous diffusion system, uranium hexafluoride, or UF6, had to move through miles of piping and thousands of stages. The gas would be pressed against barriers containing microscopic pores. Lighter uranium molecules would pass through slightly more readily than heavier ones, and the process would be repeated again and again. On paper, it was elegant. In hardware, it was brutal. Uranium hexafluoride does not behave like a harmless industrial gas. It can react violently with water vapor, producing corrosive compounds, including hydrogen fluoride. A trace of moisture inside a valve could become a chemical attack. A rough surface could trap residue. A tiny leak could contaminate equipment, interrupt production, and expose workers to a dangerous material. Steel could corrode. Rubber could swell, crack, or absorb the compound. Ordinary plastics softened, dissolved, or became brittle. Lubricants introduced another problem. Anything added to keep a valve moving might itself react with the uranium chemistry, and that so much of motion. The engineers needed a substance that could sit between moving metal parts and an aggressive fluorine compound without becoming part of the reaction. The strange white solid from DuPont offered an answer. It could be pressed into gaskets. It could be machined into valve seats. It could line small components and form seals around joints where metal surfaces alone could not close tightly. UF6 could encounter it, and in many conditions, almost nothing happened. That made PTFE valuable in the gaseous diffusion plants being designed and assembled for the war. It did not form the giant barriers themselves. Those demanded specialized metals and painstaking fabrication. PTFE appeared in the places where the system had to move, close, isolate, and survive: valves, packing, gaskets, seals, and instrument components connected to the uranium process. This was a sharp reversal of fortune. When Roy Plunkett and his technicians first found the powder inside a cylinder, it looked like the residue of a failed refrigerant experiment. It had no obvious market, no easy manufacturing method, and no convenient way to melt or shape it. Its most striking properties seemed almost useless, until engineers found a job where the material did not need to bond, conduct, or change. It only had to endure. Working with it was difficult. PTFE resisted ordinary solvents and would not flow like common plastics when heated. Parts had to be compressed, sintered, and cut with specialized tools. Each one consumed more time and money than a familiar rubber seal or polymer washer. Under normal industrial conditions, that would have been a serious disadvantage. At Oak Ridge, normal conditions had already failed. A cheap seal that dissolved in UF6 could shut down part of the plant, trigger decontamination, and delay a project racing against a war. So engineers paid for the strange material because the alternative could cost far more. PTFE did not make uranium enrichment simple. It helped stop the machinery from being defeated by the chemistry it was built to control. The result was easy to miss. White seals disappearing inside dark valve assemblies, narrow rings pressed between metal flanges, tiny parts protecting a vast plant from microscopic leaks. Elaborate so much of motion had entered a system built for national survival, not because anyone had planned its discovery, but because conventional materials could not endure the job. After the war, PTFE moved out of sealed factories and into objects people could touch. Its first familiar form appeared in the kitchen. In 1954, French engineer Marc Gregoire coated a pan with the material after his wife, Colette, suggested using it on her fishing gear. Food released with almost no effort. Eggs slid across the surface. Fish came away whole. By the early 1960s, pans carrying DuPont's Teflon name were entering ordinary homes. But the surface that made PTFE attractive also resisted nearly every attempt to use it. Paint would not hold. Glue would not grip. A coating could peel from metal after only a few heating cycles. Manufacturers had to roughen the pan, press the polymer into a prepared surface, and fuse it in place at high temperature. Some treatments chemically attacked the outer layer, so another material could finally attach without destroying the slipperiness underneath. The non-stick pan was not simply sprayed and sold. It was a carefully engineered compromise with a substance that seemed determined to stay separate from everything around it, and the kitchen was the least demanding place PTFE would go. Inside industrial machinery, small PTFE rings became bearings, sliding between moving parts without oil. They reduced friction in pumps, compressors, and control systems where ordinary lubricants might burn, evaporate, or contaminate the product. A valve could open thousands of times while the pale polymer quietly absorbed the rubbing. In chemical plants, PTFE linings and gaskets faced acids, solvents, and caustic liquids that attacked rubber, leather, and many metals. Pipes, tanks, and reaction vessels gained an inner skin, keeping aggressive chemistry away from the structure holding it. Behind a metal wall, a thin layer of white plastic could decide whether a pipe kept working or began to leak. The same material became an electrical barrier. PTFE barely conducts electricity, and it keeps that behavior across a wide range of temperatures. Thin layers wrapped around wires in aircraft, radar systems, computers, and high-voltage equipment. A cable could bend, heat up, or meet moisture while its conductors stayed separated. The coating was almost invisible. A failure measured in millimeters could shut down an entire machine. Its uses became smaller and more intimate. Medical tubing used PTFE where fluids needed a clean, low-friction path. Vascular grafts and surgical meshes took advantage of its chemical quietness and compatibility with tissue. In aerospace hardware, seals and insulation had to survive vibration, pressure changes, fuel, hydraulic fluid, and the severe cold outside the atmosphere. PTFE could help with several of those problems at once without adding much weight. That combination was the real attraction. A material that only kept eggs from sticking would have remained a clever kitchen coating. PTFE was valuable because one thin film could slip under load, block electricity, tolerate heat, and ignore chemicals that ruined its competitors. The same pale polymer could become a bearing, a gasket, or a wire jacket, depending on where engineers placed it. By the time most people recognized the name on a frying pan, PTFE had already spread through places they would never see. Inside aircraft control systems, behind chemical plant walls, beneath medical devices, and between metal surfaces where a leak could become a disaster. Its most important work was often done in silence, hidden inside machines that were never allowed to fail. But the same chemistry that kept PTFE intact inside those machines created a problem outside them. Its carbon atoms were locked to fluorine atoms by bonds so strong that heat, acids, bases, and ordinary biological processes struggled to break them apart. That strength is why the material could survive inside a chemical plant. It is also why related fluorinated compounds can remain in rivers, soil, and human bodies for years, decades, or longer. A white block of PTFE was not the same thing as every chemical in the fluorinated family. PTFE is a large, solid polymer. The broader group, now known as PFAS, contains thousands of substances, each with different structures, uses, and hazards. Treating them all as identical would erase important chemistry. But separating the compounds did not make the contamination disappear. To manufacture fluoropolymers, companies needed processing aids that could control the reaction and help move the material through industrial equipment. Some of those aids, including PFOA, could escape through wastewater, air emissions, factory residues, or discarded products. PFOA was not PTFE, yet it was connected to the industrial system that produced it. For years, these compounds traveled farther than anyone expected. They entered rivers near manufacturing sites, settled into soil, and seeped into groundwater beneath communities. So much motion. A factory could stop releasing them, but the compounds could remain in the ground long after the machinery had gone quiet. In the United States, investigations around DuPont's Washington Works plant in West Virginia brought the issue into public view. Residents described contaminated water, livestock losses, and illnesses they believed were linked to releases of a chemical known locally as C8, or PFOA. Court records, scientific studies, and later regulatory findings turned a hidden industrial practice into a national controversy. The chemistry had performed exactly as designed. It resisted attack. But a river is not a reactor vessel, and a human body is not a sealed piece of industrial equipment. Researchers began finding certain PFAS in blood samples from people far from fluorochemical factories. Some compounds moved through water, entered organisms, and persisted in the body. Studies examined possible links with the immune system, cholesterol, development, and certain cancers. The findings differ by compound and exposure, and scientists are still separating strong evidence from uncertainty. Still, one fact was difficult to ignore. Chemicals built not to disappear were turning up almost everywhere scientists looked. Manufacturers phased out PFOA and PFOS in many countries, but replacements raised a harder question. If a shorter chain compound leaves the body faster, does that make it safe? Not necessarily. It may travel more easily through water, require larger amounts, or carry risks that are still being studied. And removing one compound does not remove what it already left behind. Contaminated equipment remains. Old firefighting foam sits in storage. Landfill liquid seeps downward. Polluted aquifers keep spreading beneath the surface. That became the modern dilemma of fluorinated materials. Their durability saves lives, prevents leaks, protects electronics, and extends the life of tools. The same durability can make a spill difficult to clean, a product difficult to destroy, and a manufacturer's responsibility difficult to end when the factory gates close. Burning ordinary waste can destroy many chemicals. PFAS waste may require specialized high-temperature treatment, careful capture systems, and proof that dangerous byproducts have not simply moved into the air. Digging up contaminated soil can spread the problem. Pumping polluted groundwater can take decades, while the carbon-fluorine bonds remain in place. A material designed to refuse almost every attack had crossed an invisible boundary. In a machine, persistence was protection. In the environment, persistence could become pollution. But the cylinder did not hand anyone a finished product, it handed them a problem. Roy Plunkett had found a white, waxy solid where a gas should have been. He could scrape it from the vessel, weigh it, and prove that heat and chemicals barely touched it. But a lump of stubborn material was not yet a seal, a wire coating, or a pan surface. It had to be shaped, made to stay attached, and produced in quantities larger than a laboratory handful. That was where the accident ended and the engineering began. The first obstacle was processing. The new polymer did not behave like ordinary plastic. Melt it in the familiar way, and it refused to flow. Try to dissolve it, and common solvents slid off without effect. It would not soften, so workers could pour it into a mold. Engineers had to develop methods that worked with its resistance rather than trying to defeat it. They learned to compress the powder into blanks, heat those blanks until the particles fused, and machine the solid shapes afterward. For wire, the challenge was even more delicate. The material had to be forced around metal without losing its smooth, insulating surface. A substance that resisted almost every chemical attack also resisted ordinary manufacturing. The chemistry had to be controlled, too. Producing the starting gas safely required dedicated equipment, careful pressure control, and systems that could contain a highly reactive process. Then came purification, particle size, heating cycles, and quality checks. A small variation could change how the powder compacted or how firmly a coating held to a surface. By the 1940s, DuPont and its partners were no longer asking only, "What is this?" They were asking harder questions. Could it be made reliably? Could it be cut into gaskets for valves? Could it insulate cables in military equipment? Could a customer use it without knowing the strange chemistry behind it? The answers arrived piece by piece. Kinetic chemicals began commercial production in 1946, and the material, later sold under the name Teflon, moved from sealed laboratory vessels into industrial seals, electrical insulation, and chemical processing equipment. Decades later, it reached kitchens, where its slipperiness became a selling point instead of an engineering obstacle. The famous accident created the substance. It did not create the technology. That took years of learning how to attach the untouchable, shape the unworkable, and manufacture a material whose greatest talent was refusing to cooperate. And that is what the cylinder left behind. Not an empty container, but a contradiction. The gauge had fallen silent. The gas seemed to have vanished. Yet inside the steel, its molecules had rearranged themselves into a solid that could shield a machine from heat, keep a valve from failing, and later slide unnoticed into the pan beneath a household breakfast. Then the same property that made the material useful revealed its darker edge. The bonds that kept heat and chemicals out also made the new solid stubbornly difficult to retrieve, destroy, or contain after it escaped. Protection and persistence came from the same chemistry. When the lid came off, the experiment looked like a failure. Pressure gone, gas absent, plan ruined. But the gas had not disappeared. It had become the thing inside the steel. The cylinder was never empty. It was the first place a new material learned how to outlast its makers.